So in the previous introductory class of wave-particle duality, we have talked about the de Broglie hypothesis. And if you remember, we have said that whenever a particle is in motion, that means it must have some velocity, then a wave is associated with that particle. And we call that wave, which is associated with a particle or matter, as matter wave or pilot wave, because it is assumed that this is the wave which guides that particle. That's why this wave associated with a particle in motion is called matter wave or pilot wave. And according to de Broglie hypothesis, the wavelength of that wave equals to h by p, where h is your Planck's constant, 6.626 × 10⁻34 joule second, and p is the momentum of that particle. That means it can be written as h by mv, and m is the mass associated with the particle when its velocity is v. Okay, remember one thing, this mass is the mass of the particle when its velocity is v. Why I am telling that? Because now you know that mass of a particle varies. When the particle is at rest, its mass is m0, which we call as rest mass. We call it as rest mass because particle is at rest. But when the particle is moving with some velocity, then the mass changes. And I am saying that mass is same, which is greater than this rest mass. Generally, for our physical world, we do not observe the change in mass because the velocity is less. When the velocity is higher, that means it is comparable to velocity of light in free space, that is 3 × 10⁸ meters per second. Comparable means when you cannot neglect that velocity in comparison to velocity of light, then mass change will be significant. That means this m will be significantly different from m0. So this is your de Broglie hypothesis. Lambda equals to h by p. So by this hypothesis, the wave nature and particle nature are associated. Wave nature and particle nature are associated with this formula. This is called hypothesis because it is theoretical development. Though, as I have said earlier, that after the hypothesis, it was experimentally verified by two scientists, Davisson and Germer, which we will discuss today also. And another point, this matter wave associated with the particle has only one basic characteristics, and the characteristic is the particle must be in motion. It doesn't matter whether the particle has some charge or it is neutral, and it is completely different from the wave we know about, like we know about light, we know about any type of electromagnetic wave like X-ray, gamma ray. This matter wave is completely different from this type of electromagnetic wave. And since we always say that the particle is associated with the wave always, that means wherever the particle goes, the wave follows. That's why the velocity of the particle is same as velocity of the wave. If I say velocity of the wave as vg, then and velocity of the particle as v, then v should be equals to vg. From a logical sense, we will prove it. And what we have also studied, that we can get this formula lambda equals to h by p from the concept of E equals to h nu and the total energy as root over p square c square plus m0 square c to the 4. That means relativistic energy. If we talk about relativistic energy, then this is the expression of that energy, and from our Planck's law, from the photoelectric effect, we know that energy associated with a photon is h nu. From these two, we have observed that we can get that lambda equals to h by p also. Okay. Now, we will derive the same de Broglie hypothesis from another known formula, which each of you know about, the Bohr theory. So now we want to derive de Broglie hypothesis from Bohr theory. And what was Bohr theory? If you recall, so we want de Broglie from Bohr theory. If you remember, as per Bohr theory, an atom is composed of nucleus, which is at the center of the atom, which is positively charged due to presence of protons, and there are several electrons surrounding that nucleus in several orbits. Some particular orbits exist through which the electrons can rotate around the nucleus. Okay, so we suppose this is your nucleus, the center, and an electron is rotating around it in a path. Suppose this is an electron. This is an electron. Electron is rotating around that nucleus in this circular path. Since the motion is considered to be stable, every event after each revolution around the nucleus repeats precisely as before. That means, suppose the electron is at this point. The electron, I'm drawing it. Suppose electron is at this point at a particular instant. At some time, electron is at this point during its motion around the nucleus. So it goes along this direction, say, and covers a complete rotation. That means it starts from this point, completes the rotation, and comes back to the same point after some time interval, say t. After some time t, the electron completes one rotation. So it has started from this, not started, so we have observed that electron at some instant at this point, and it comes back to that same position after the interval t, say. Next, if we observe the electron, we may see that the electron completes second rotation and comes back to the same point again after the same interval t. That should be because electron has a particular time period of rotation, because its motion is stable. That's why I'm saying that since its motion is stable, every event after each revolution, so this is your event, this event repeats itself after each revolution. So if the electron be at this point at any instant, it would be at the same point after each revolution. After each revolution, we can observe it at this point. Therefore, if we assume that de Broglie hypothesis is correct, that means a wave is associated with a particle. So we can observe a wave is drawn. So this wave we assume is associated with that electron which is rotating around the nucleus. Therefore, this wave must be in such a way that this wave always, that means we can say that this wave associated with the electron must have the same form at that point after every revolution. That means if we observe this point, that means electron was initially present at this point, and after one complete rotation, it comes back to this point again. Then what is the part of the wave associated with that electron at this position? We observe this is the highest point of the wave. That means we call it crest. So this is a crest point. So it is a crest. So after one complete rotation, what do you expect here? Crest. So after each revolution, after each revolution of the electron, we can expect the crest here. Similarly, if we observe, suppose this point, what is the portion of the wave associated with this region? We observe is the trough region. So after each revolution, it is expected to get this trough at this point. So in simple words, if you want this consistency, then the orbit must accommodate an integral number of waves. That means if I draw it in this way, suppose this is the path of the electron and the wave associated I am drawing in this way. Arbitrarily I am trying to draw, and you observe I cannot accommodate a particular number of waves. We cannot connect them. There is a discontinuity at this point. So it is not possible. This is not possible. Only if the wave is drawn in such a way that you can have a particular number of waves accommodated in this region. That means how many waves are accommodated in this region? Like, say this is the initial part of the wave. So this starts. How do we draw wave? How do we draw? This is how we can draw a wave. And how many waves we can say? This is one wave, the bold one. So this is one. That means here we start from this point. If I start from this point, this is one wave, then second wave, then third wave. We can count up the number. Say number is 10. That means 10 waves are accommodated for this radius Rn. That means for this circumference. This circumference, what is the circumference? Circumference is 2 pi Rn. The circumference means the length the electron covers. The length the electron covers. That 2 pi Rn covers, say, 10 number of waves. 10 number of waves. That means what will be the total length? This length is lambda. This length is lambda. So this is 1 lambda. So 2 lambda, 3 lambda. We can count how many lambdas can be accommodated within this circumference. Suppose we can say there are 10 lambdas. That means we can say 2 pi Rn equals to 10 lambda. When the electron is moving 2 pi Rn length, then the wave must be covered 10 lambda distance. Therefore, in general, we can write it that 2 pi Rn equals to n lambda, n any integer, 2, 3, 4, 100, 2000, 5000, 2 lakh, whatever. Depending on the value of lambda, n can be different, but n must be an integer. Because if n is not integer, then we'll observe this type of situation, which is not desirable. So, what we get from this logical concept that Rn, the radius of the Bohr orbit, is n lambda by 2 pi. Radius of the Bohr orbit is n lambda by 2 pi. Now, according to Bohr theory, the electrons can rotate around the nucleus in certain orbit. And what is that condition of that orbit? The condition was that angular momentum of the electron must be an integral multiple of h by 2 pi. If you remember, angular momentum is mv_rn. The angular momentum is equals to integral multiple of h by 2 pi as per Bohr theory, which we have studied in class 11 or 12. So from that we can rewrite it. What is mv? Mv means momentum. So I can write p. Instead of Rn, we can write this one. So n lambda by 2 pi equals to nh by 2 pi. 2 pi cancel out, n cancel out. What is left? Lambda equals to de Broglie hypothesis. So only with the help of 2 steps from Bohr theory, we can get de Broglie hypothesis also. So all these theory are interrelated, they are interconnected. If you understand one theory, you can derive the other. So no problem. So this is your de Broglie hypothesis, by which we can connect the wave nature with particle nature. Now, we want to find out, say, the de Broglie wavelength of a particle. De Broglie wavelength of a particle, that means when the particle is assumed to form a wave, what is the wavelength of that particle? That we want to know. So, to know that, what we have observed, that if we want to estimate the wavelength of the de Broglie wave, that means lambda equals to h by p. That means you need to know momentum of the particle. If you know the momentum of the particle, then only you can estimate the wavelength associated with the matter wave. Now, if momentum is given, no problem, you can estimate. But instead of momentum, if kinetic energy is supplied, that means if kinetic energy is supplied, then how will you estimate the wavelength of the particle? Or if, say, a potential difference is supplied, to you. That suppose a particle is accelerated by supplying a potential difference of 2 volts. What is the wavelength associated with the particle? That means you need to somehow connect this kinetic energy or potential energy with wavelength. So how will you do that? There are two approaches. First, we'll discuss both. Then I'll tell you which to use when. The first approach is the normal case, non-relativistic approach. First one we call non-relativistic approach. Non-relativistic approach means we have said that generally whenever particle is in motion, we use Newton's theory, Newton's law of motion, which you are studying from your class 7 standard. But we have also observed now that in some situations, especially when we are using subatomic particles like proton, neutrons, electrons, for those particles which are very, very, very tiny and have some velocity, for those particles, the general Newtonian mechanics cannot be considered. For that, we require Einstein's relativity. And what was the basic difference? Remember, I told you that in normal case, that means in Newtonian mechanics, whenever we talk about energy, the total energy is sum of kinetic energy and potential energy. Whereas in case of relativistic mechanics, kinetic energy is there, but instead of potential energy, you have the rest mass energy. That means when the particle is at rest, then also it has some energy. That energy is the rest mass energy. And accordingly, we get some equations. So first, we are not considering that relativistic approach. Non-relativistic approach, that means normal Newtonian theory. So as per non-relativistic approach, that means general Newtonian theory, what is kinetic energy? We know kinetic energy means half mv square. Just a second. Kinetic energy is half mv square. That is known. So I am writing kinetic energy is half mv square. Or since momentum is mv, instead of v square, we can write p square by m square. That means p square by 2m. Due to presence of this m, we have kinetic energy equals to p square by 2m. And if kinetic energy is p square by 2m, then what is p? P will be root over twice m. Okay. So as per Newtonian mechanics, momentum is related with kinetic energy by this formula. All of you know it. Therefore, what will be the wavelength? Lambda equals to h by p. Now just put the value of p. So lambda equals to h by root twice m. Okay. That is your formula. In fact, you need not to remember the formula. You can derive it in a second. Lambda equals to h by root 2m ek. So if the kinetic energy of the particle is supplied, suppose kinetic energy is given as 1 joule. So we'll put ek as 1 joule, put mass of that electron or the particle whose mass we require, and Planck's constant. If you put those values, you can estimate lambda easily. So if kinetic energy is directly supplied, you can estimate the wavelength of the particle very, very simply. Okay. But suppose sometimes instead of kinetic energy, potential difference is supplied. What is meant by that? Think of it generally. That there is a circuit. Say I'm giving a simple circuit, a resistance, a key, a battery. Simple circuit. You are supplying, say, V volt. Suppose you have connected a small battery of 2 volt supply. So this is V equals to 2 volt. And so whenever the key is switched on, current flows through the circuit. What is the direction of current? This is the direction of current. That means electrons are flowing in this direction. This is the direction electrons are flowing. So my point is electrons are flowing, we are saying, because what is current? Current is nothing but flow of electrons. So electrons are flowing. That means electrons are moving. Electrons are moving throughout this circuit. That means they have some kinetic energy. As simple as that. If we do not have the kinetic energy, we cannot move from our place. So whenever we are moving, we must have some kinetic energy. So electrons are moving, electrons must have some kinetic energy. But where from do these electrons get this kinetic energy? Who is supplying the energy? Electrons cannot derive their kinetic energy. They cannot originate their kinetic energy. They cannot produce their kinetic energy. So who is supplying that? The battery, of course. The battery is supplying the kinetic energy. Battery is supplying the required kinetic energy to the electrons. So what is that amount of kinetic energy? Say E is the kinetic energy of the electron. So how can you relate it with the potential difference supplied? If you remember how potential difference is defined in your class 12. Suppose potential difference between 2 points A and B. In your course stream in electronics, you have to deal with this potential throughout your life. What is potential difference? Potential difference between the point A and B is defined as the work done to move a unit charge from the point A to B or B to A, depending on the direction. Potential difference between these 2 points A and B is the amount of work done to move a unit charge from the point A to B. So this is the work done. This is the work done to move an unit charge from the point A to B. Therefore, if the charge is E, then what will be the work done to move that charge from the point A to B? Potential difference into E. Get my point? Again, what is V? The potential difference between these 2 points. Potential difference means the work done to move unit charge. Unit charge means charge value 1. Work done to move a unit charge from point A to B. That is potential difference V between these 2 points. Therefore, what will be the work done to move this charge E? E into V. So total work done is E into V. So you are doing some work. What is the amount of work? EV amount of work you are doing to move a charge E from the point A to B. And that work done is stored as the potential energy. So whenever you are connecting a battery to an external circuit, that means you are supplying the potential energy to the circuit, and that potential energy is actually converted into the kinetic energy. Therefore, that when you are saying the electrons are moving, that means electrons must have some kinetic energy, and this kinetic energy they got from the potential energy as supplied by the potential difference or battery V. So what will be the potential energy supplied to a single charge E is EV. This is the potential energy supplied to a single charge E, and this amount of potential energy is converted as kinetic energy of the electrons. So each electron has this energy EV. So always understand that whenever a charge is moving with some kinetic energy, then it has acquired the kinetic energy from the potential difference supplied. So you have supplied the potential difference V and charge of electron is E. Therefore, total potential difference supplied is EV. What we can say, the total potential energy supplied is EV, and that potential energy is converted into kinetic energy of that electron. Therefore, lambda equals to H by P, and we have already found that this P can be written as twice M Ek. Go to the previous slide. H by twice M Ek. Therefore, we can write lambda equals to H by root over twice M. Now, instead of kinetic energy Ek, we can write Ev. So, with this formula, we can find out the potential, find out the wavelength or de Broglie wavelength for any particle if the particle is accelerated by a potential difference V. That means, suppose you are asked that an electron is accelerated by supplying a potential difference of 5 volt. What is the wavelength associated with that electron? That means this V is supplied as 5 volt. Battery connected is 5 volt. All the quantities you know, you can estimate lambda. Again, my suggestion at the time of exam, you have to put so many values. So my suggestion, do it now. Put the values 6.626 into 10 to the power minus 34 joule second, that is H, by root over twice mass of electron. We are talking about Newtonian mechanics, so there is only one type of mass. There is no concept of rest mass here. So only one type of mass. Mass of electron is 9.1 into 10 to the power minus 31 kg. I am writing all the quantities in SI. Charge of electron, you know, 1.6 into 10 to the power minus 19 volt. 19 coulomb into V. So this is in meter, because all the quantities are in SI. Therefore, wavelength should be in meter. If we put these values, you will get the value as 12.27 by root V in angstrom. That means 12.27. If you calculate this value, my suggestion, do it once at least. Do it once with your calculator to check whether you are getting this value or not. So if you calculate that portion, you will get 12.27 into 10 to the minus 10 meter by root V. This V. So we can write easily that lambda equals to 12.27 by root V angstrom. If you can remember this value, then your calculation will be much easier. At the time of exam, you just put the value of V and get the answer. Like if you are said, suppose an electron is accelerated by 100 volt, what will be the wavelength associated with that electron? So you just put 100 here, that will be 12.27 by 10, that means 1.227 angstrom. Easy. So this is the relativistic approach, non-relativistic approach. So if we use normal Newtonian mechanics, then we get lambda equals to h by root 2m ev form. Oh, by the way, instead of numerical, they may ask you to find this one, prove this, or find out the relation between wavelength and potential difference for a particle which obeys non-relativistic mechanics. So you can find it out. Now situation will be slightly difficult when we consider relativistic approach. Next, relativistic approach. That means we cannot write down the kinetic energy directly as p square by 2m. No. Because now our energy is sum of kinetic energy and rest mass energy. Again, what was rest mass energy? When the particle is at rest, then the energy possessed by that particle is rest mass energy m naught c square. This is the rest mass energy. We can do it. Now, what is the objective? Our objective is to find out a relation between kinetic energy and momentum. Because in the formula of Broglie, lambda equals to h by p. We need to substitute that p in terms of Ek. Clear? So what we will do? First thing, we square both sides. So it will be E square equals to Ek plus m naught c square square. Okay. That means, what is E square? From relativistic mechanics, we know E square equals to E square c square plus m naught square c to the power 4. From the relativistic mechanics, we know E square equal to p square c square plus m naught square c to the power 4. Use it. So this is E square equals to, now right hand side is E k square. Just a second. Use the user. Ek square a plus b whole square plus twice Ek m naught c square plus m naught square c to the power 4. Now observe, cancel out. M naught square c to the power 4 cancel out. Therefore, E square equals to this. That means, if I take the square root, Pc equals to root over Ek square plus that. I am taking Ek common, so that I need not to write it so many times. So Ek plus twice m naught c square. So this is your Pc. And what is the objective? Objective is to find out lambda. So lambda is h by p. That means it can also be written as hc by pc, because we have pc here. Now put the value. It is hc by root over ek plus twice m naught c square. So this is your lambda. So this is the wavelength of that particle when the kinetic energy of the particle is known. Similarly, so this is relation between wavelength and kinetic energy. Now, if we require wavelength, relation between wavelength and potential difference, then lambda equal to hc. We know that kinetic energy Ek equals to ev. Whether it is relativistic mechanics or non-relativistic mechanics, That is always true. So instead of Ek, we can write EV plus twice m naught c square. So this is your formula for the wavelength of that particle when the potential difference is supplied, EV. V is supplied, then you can estimate wavelength of that particle easily through this equation. So you observe we have the relation between wavelength and kinetic energy, or wavelength and potential difference by two approaches. This is one formula, and we have estimated another formula, this one. This one is derived for non-relativistic case, this is derived for relativistic case. Then when will we use it? If it is not mentioned, suppose if it is mentioned that find out the relation between wavelength of a particle when it is accelerated by a potential difference by relativistic approach, find it out by relativistically, then we can directly use this relativistic approach and get this formula, no problem. Or if we require the numerical value, we can put the values, get the value of lambda. But if it's not mentioned, suppose the question is a particle is moving with a particle is accelerated with 5 joule of energy, or a particle is accelerated by 10 volt potential difference. What is the wavelength associated with the particle? Then confusion comes, because now you can think which of these two equations will you use, whether you will use relativistic approach or non-relativistic approach. Understand it that we can use non-relativistic approach for normal particles. That means if it is a cricket ball, if it is a marble, if it is a small object, say of 0.1 milligram, then also we can use non-relativistic approach. Whereas when the particle is subatomic particle, like whenever the particle is electron, when the particle is proton, then you use relativistic approach. Or if you still confused which one to use for your numerical, then always use relativistic approach, because from this relativistic formula, we can get back to that non-relativistic formula. It is more precise for it. That means if we use this formula for a cricket ball, you get some answer, and you will observe that answer will be same as the answer obtained from this formula. You will get the same answer if you use relativistic approach formula. So if you are not sure which one to use, then always use relativistic approach formula. Okay. Next, the experimental verification. As I have said you earlier, that de Broglie formula is just a hypothesis, is just a theory, and no theory is accepted unless it is experimentally verified. And that verification was done by two scientists called L.H. Germer and C.J. Davisson. So it is known as Davisson-Germer experiment. So we will discuss that experiment, how the experiment is done, and why that experiment was so successful. I'm showing you a YouTube video first. That YouTube video is also shared in your Canvas profile. You can observe it under the head of module 1. Can you see it? I have not started it yet, but
Yes,
can you see the screen? Okay.
Yes, sir. Yes, sir.
Tell me whether you can hear the sound. Can you hear the sound?
No, sir.
Oh, okay. Let me.
Wave and particle characteristics. According to this
Can you hear the sound?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Otherwise,
Yes, sir.
otherwise, I have problem. Okay. There's no problem.
Yes, sir, we can hear.
Okay, thank you.
Related that all forms of matter have both wave and particle characteristics. According to this hypothesis, electron, just like light, have a dual particle wave nature. Two American physicists, C.J. Davisson and L.H. Germer, were the first to experimentally prove the wave nature of material particles in 1927.
In fact, after this experimental verification in 1927, Broglie was awarded Nobel Prize. Before 1930, probably in 1929, he got his Nobel Prize.
Displayed here is a block diagram of the experimental setup used by Davisson and Germer. It consisted of a nickel chloride crystal, the target, an electron gun, G, and a detector. The electron gun produced a beam of electrons. The electron gun used by them consisted of a tungsten filament, F, and high and low tension batteries. The low tension battery was used to heat the filament. The red hot filament produced an electron beam. A high tension battery was provided to accelerate the electron beam. The detector or the electron collector moved on a graduated circular scale. A sensitive galvanometer was also connected to the detector. How did they perform the experiment?
Okay, so what was the experimental setup? Experimental setup was very simple. You require a crystal. This is your crystal. Here they have used nickel chloride crystal, NaCl, salt. NaCl, salt, your normal salt. NaCl crystal is used. And electron should be incident on this crystal. And they want to observe whether these electrons which are incident on this nickel crystal shows its particle nature and wave nature. But remember one thing, in a single phenomena, both nature cannot be revealed. You cannot observe both particle nature and wave nature in a single phenomena. So what they do, they use two different phenomena. One, the Broglie hypothesis, that is that formula they used when electrons or electron beam, better to say, hit that nickel crystal chloride. And second, they use the concept of X-ray diffraction, which is completely a wave nature of light. And they utilize these two, and from these two formula, they get some value of lambda and compare that lambda. We'll discuss it. But what are the requirement? So one thing, crystal is required because Bragg's law should be introduced here. And for Bragg's law, we require some crystal. So the crystal is provided by this NaCl crystal. Next, electron gun. The electron gun means simply a coil, and when the coil is heated, then electron will be produced. And for that heater, they are using low tension battery. So this one, low tension battery, will provide the potential to the tungsten filament. That means it will heat the tungsten filament so that electrons are generated. But whenever electrons will be generated from this filament, they will go in all arbitrary direction. That means some electrons are going in this direction, some are going in this direction, and so and so. But we require electrons to move in a particular direction. We require electrons to move in this direction only. That's why another battery used, high tension battery, which will guide the electron in this direction, so that they will not go in arbitrary direction. They will go in a particular direction. That means this high tension battery is used to focus the electrons. So electrons incident on this nickel chloride crystal. Then they will be reflected in all possible directions, and that amount of electrons are collected by this detector. It is called Faraday cup. This one collects that electrons going in a particular direction, and through this circular scale, this detector can be moved. Okay, so again, observe it.
The electron beam was made to pass through a pinhole and made to strike the crystal normally. The electrons scattered in all directions, acting like waves. They observed that at certain angles, the detector indicated a peak in the intensity of the scattered electron beam. This maximum intensity was due to constructive interference, a phenomenon confined only to waves. Thus, they experimentally proved the wave nature of electrons. Davisson and Germer plotted a graph taking the angle between the incident and scattered direction of the electron beam, phi, along the y-axis and the intensity of the scattered beam at different values of accelerated potentials along the x-axis. The nature of the graph is shown here. From the experimental curves obtained, the following conclusions were drawn. Intensity of scattering depends upon the angle of scattering, phi. A bump or kink always occurs in the curve when phi is equal to 50 degrees. This bump or kink increases as the accelerating potential difference is increased. At 54 volts, this bump is maximum and then it decreases on further increase of potential difference. This peak indicated the wave behavior of the electrons.
What they measured? They have measured two different quantities. One, the angle phi. What is phi? Understand it. Phi is the angle between incident ray and diffracted ray. Phi is the angle between incident ray and diffracted ray. Let me suppose, okay, I'll show you in the diagram. It will be better to understand. So remember, phi is the angle between incident ray and diffracted ray. Or for your understanding, you can think it is angle between incident ray and reflected ray. Incident ray and reflected ray, the angle between these two, that is phi. And they also measured the intensity of the scattered wave. You observe there are two batteries connected. One is to heat that filament. Now more heat you supply, that means more potential difference you supply to the filament, more electrons will be produced. So that is the V. If you increase that V, more electrons will be created, more incidence, more collection of electrons. Clear? So that is your V. So what they have done for a particular V, say 44 volt, that means filament is heated by 44 volt first, and they have measured the angle between incident and scattered or reflected ray by moving that detector, rotating the detector. You can change the angle phi, and for different phi they plotted it, and it is observed that there is a kink. There is a kink, this kink. There is a kink or hump, whatever you say, that occurs when the phi value is 50 degree. This is one observation, important observation. So note down that kink or bump occurs when the phi is 50 degree. So this is first observation. Note it down. Second observation, if we increase the potential difference, say from 44 volt to 48 volt, you will observe kink has increased. The kink which occurs at 50 degree increases. Now increase the potential difference from 48 to 54, you observe more amount of kink. Now if you continuously increase, you will observe that after 54, the kink stops increasing, it's decreasing now. That means maximum kink occurs at 54 volt. So that means in terms of diffraction, the central diffraction pattern is observed at 50 degree for potential difference of 54 volt. So these are the 2 points we have noted from Davisson and Germer experiment. Okay, I will explain why we have noted these values, but before that thing, I will show you another video. This one.
Bulb. And the biggest risk of using this equipment is probably that you might break this if you don't handle it with enough care. At this end, we've got an electron gun, a heated filament which releases electrons, which are attracted to the anode here, where they pass through a small hole and create a narrow beam, which travels across the tube and strikes.
This is like the previous case. Only we have a beaker here, and again we have some low tension and high tension battery, because one battery is being used to generate electrons and other battery is being used to focus the electrons. And there is a crystal connected at this point. There is a crystal connected here at the center. And here, as he is mentioning, you can observe the spectrum here. That means you can observe the diffraction pattern at this region. Observe it.
Across the tube and strikes the fluorescent screen here.
This fluorescent screen.
Now in this tube we've got a thin sheet of graphite here in the path of the electrons, and it's this which causes the electrons to be.
So instead of nickel crystal here, or NaCl crystal here, graphite is used.
diffracted. Now, in order to use this, we need an extra high tension, or EHC, voltage supply, and a separate circuit. Supply here. Now, before doing anything else, I make sure, and the voltage controls. I then connect the 0.
I'm skipping the connection points.
That there aren't any by switching on the cathode, which takes a little while to warm up, but there you go, you can see it starting to glow now, which means you can turn on the high voltage supply.
Electron has been produced.
And I'm going to turn that up to about
Now they are
3000
focused.
volts.
This is
Now,
the
what I hope you
diffraction
can see is a green dot surrounded by fainter concentric green circles. And that's a diffraction pattern that's produced as the electrons fly through the graphite. Now, you can increase the energy of the electrons by increasing the voltage. You can see that's changed the diffraction pattern. The rings are closer together. And that's because at increased energies, the electrons have a shorter wavelength and they're diffracted less by the graphite. There's one more thing you might want to do with this apparatus, and that's to convince your students that the pattern is genuinely produced by electrons, that is, charged particles, and not by a beam of light. And to do that, you use a magnet. And if you bring that close to the beam, you can see that it deflects the image on the screen. And that certainly wouldn't be happening if it was being produced by a beam of light. Now, once you're done with the apparatus, obviously you turn it off, but it's best to wait a few.
Okay. So, what we have observed in Davisson-Germer experiment, that the maximum diffraction occurs at a particular potential difference, 54 volt, and at a particular angle phi as 50 degree. And again, what was phi? If this was the direction of incident ray, and after scattering, suppose it is scattered at this point and goes along this direction. So phi means this is the angle. Phi means this is the angle. Angle between incident and reflected or scattered beam. Angle between incident and scattered beam. So this is your phi. So these are the two things you have now. Now with the help of this, you need to check whether de Broglie hypothesis is correct or not. Now from de Broglie hypothesis, we know lambda equals to h by p equals to, we have the formula. If I just use normal non-relativistic for simplicity only, 12.27 by root v. So I'm writing 12.27 by root v in angstrom. If I use relativistic approach formula, it will be more correct, but it will take some time. So I'm first using this basic formula. So by 54, this angstrom. If we put these values, you get the value as 1.67 angstrom. Check it with your calculator. It is 1.67 angstrom. That means wavelength of the de Broglie wave associated with the electron is 1.67 angstrom. Yeah. Next, we forget about de Broglie hypothesis. We consider that electrons are waves only, as if there was no condition that electrons can be particles. So what we say, that some light is incident on this is NaCl crystal. This is a different layer of the NaCl. This is NaCl crystal. This is the different layers. That means this is first plane, this is second plane, this is third plane. Different layers or planes of the NaCl. So one beam is incident and incident at the first plane and reflected along this direction. This angle between that is we have measured as phi. Another beam passes through the first layer, comes to the second, and then refracted. If the distance between two consecutive layers is d, then according to Bragg's law is only applicable for waves, remember. So according to Bragg's law, 2d sine theta equal to lambda or n lambda. We are considering n equals to 1 because at that value n equals to 1, we get maximum diffraction, and this condition is maximum diffraction condition. And what is this theta? Theta is this angle. This is called glancing angle. Angle of the incident ray with respect to the ground, with respect to the plane. So this is theta. So 2d sin theta equal to lambda. So from that we need to estimate lambda. So 2d theta we do not know. Theta we do not know. What we know? We know phi. Phi is known. Now we know that for a plane this whole angle is 180 degree. This is the angle. This one is theta. This is incident, this is reflected, this is theta. Then this will be also theta. Angle of incidence equals to angle of reflection. This angle is phi. Then you can relate between theta and phi. So 2 theta plus phi equals to 180 degree. That means theta is 180 minus phi by 2. That is your theta. So put the values. 2, please note it down. These values you may not find in books, though the general experiment you can observe, you can read from any book. But the value, the way I am calculating it, may not be found in books. Now this D means interplanar spacing. Now for NaCl crystal, this value of D, please note, is 0.909 angstrom. D equals to 0.909 angstrom. So D is this sine 180 minus 50 by 2. Calculate it. If you do the calculation, I am sure you get this value 1.65 angstrom. So we observe. Therefore, lambda is estimated by 2 different ways. First, lambda is estimated from de Broglie hypothesis, which says that wave and matter are connected by this formula, lambda equals to h by p. And if we use de Broglie hypothesis, then we get the wavelength associated with electron as 1.67 angstrom, when the potential difference applied is 54 volt. And in that experiment, since we have observed that maximum peak occurs at an angle 50 degree, where this angle is the angle between incident and reflected beam, then if we assume that those electrons produce a beam, a wave, then we can use Bragg's law as 2d sin theta equals to n lambda. For maximum diffraction, n is taken to be 1. Therefore, lambda can be calculated from Bragg's law, and that lambda is estimated to be 1.65 angstrom. So these two wavelengths estimated by 2 different techniques are very similar to each other. They are very close to each other. So the change you are observing is may occur due to experimental conditions. In fact, with higher precision, with better instruments, that difference is reduced much. So the point is, by these two techniques, we have observed the almost same value of wavelength, which proves that de Broglie hypothesis, that is lambda equals to h by p, must be correct. So that was your Davisson Germer experiment. So experimental procedure is very simple. Then what you have to do, you have to calculate lambda from de Broglie hypothesis. So you have to put just the value of lambda equals to 12.27 angstrom by root v. V is 54 volt. Put the values, you get the 1.67 angstrom value. Then you need to use Bragg's law, that is 2d sin theta equals to lambda. Only thing here you need to remember is the value of D, which is 0.909 angstrom for NaCl, and this theta should be written in terms of phi. So total angle is 180 degree. Therefore, this theta, that means angle of incidence and angle of reflections are same. That means these two thetas must be same. So 2 theta plus phi equals to 180 degree. From that, we have written the value of theta in terms of phi. And if you calculate it, it comes out to be 1.65 angstrom. So this is the way we can verify de Broglie hypothesis. Okay. Next, let's do a numerical. Or better to before numerical and analytical problems. Say the problem is, please note it down. An electron of rest mass m naught possesses de Broglie wavelength equal to its Compton wavelength. Proof that its kinetic energy equals to root 2 minus 1 m naught c square. Interesting question. What is said that an electron is there whose rest mass is m naught. Now it has a condition. The condition is that since you cannot think of an electron which is at rest, so there must be a de Broglie wavelength associated with that electron. Again, when we discussed Compton effect, we know that there is a Compton wavelength associated with each particle. So electron has a Compton wavelength. We know the value actually 0.02427 angstrom, which we have used in different numericals. So here in this particular case, it says that Compton wavelength and de Broglie wavelength are same for a particular electron. Then you need to find out the kinetic energy of that electron. So if I say this is lambda is the de Broglie wavelength and lambda c is the Compton wavelength, these two are same. That is given. De Broglie wavelength and Compton wavelength are same. Utilize it. What is de Broglie wavelength? Lambda equals to h by p. Put it. And what was our Compton wavelength? H by m naught c. Be careful. It was h by m naught c. Okay. So from that, what we can say? Numerator same. Therefore, p must be equal to m naught c. P must be equal to m naught c. Now, what we require? We require kinetic energy. We require kinetic energy in this form. And you observe in the kinetic energy, m naught is present. We know that kinetic energy can be written in two ways, either relativistically or non-relativistically. But if we write non-relativistically, then m naught should not be present, because in case of non-relativistic kinetic energy, it will be only half m v square or half m naught v square. You cannot observe m naught c square. Therefore, here it is expected that we will use relativistic mechanics. So, we will use P equal to m naught c. Now, if first thing we require kinetic energy. Kinetic energy means, remember we have written it earlier. That total energy equals to kinetic energy plus rest mass energy. That means kinetic energy equals to total energy minus rest mass energy. What is total energy? Total energy is E square C square plus m naught square C to the 4. That is the total energy minus rest mass energy. So kinetic energy equals to total energy. This is total energy minus rest mass energy. So this is your EK. Then this is simple. So kinetic energy equals to root over P square C square. Now what we have observed from the condition, P equal to m naught C. So put it. It is m naught square C square, again C square. So C to the 4 plus twice m naught square C to the 4 minus m naught square. Sorry, not m naught square. M naught C square. So here what we get? Root 2 m naught square C to the 4. That is taken outside of the root. So it will be m naught C square minus m naught C square. 2 minus 1 m naught C square. Simple. Only what we have used? We have used the concept of relativistic mechanics. That total energy is sum of kinetic energy and rest mass energy. That concept is used. Is there any query? Is there any query regarding it? If you have any query, ask me now. How this kinetic energy is derived? Is there any question? Then now the question is, say, if Compton wavelength of an electron is same as its de Broglie wavelength. If Compton wavelength is same as the same as its de Broglie wavelength, find the velocity of that electron. That is the question. If Compton wavelength of an electron is same as its de Broglie wavelength, find the velocity of that electron. Do it. From that, we can write mv equals to m naught c. And what you have done to get the value of c, you have cancelled m with m naught. That is possible in the physical world because mass remains constant. Mass doesn't change drastically. But we are talking about electron, subatomic particle. When a subatomic particle is in motion, like here it is moving with a velocity v, then its mass is not same as rest mass. That is the trick in this question, that this mass m is not same as rest mass m naught, because we are talking about electron. It's not a treated ball. If it is a treated ball, then the masses would be same, but it's not here. And how this m is related with m naught? M means m naught by root over 1 minus v square by c square. Remember, we have talked about how this mass is related with rest mass m naught, and that's why I have told you that when this v is very very small, then we can neglect v square by c square. If v is very very small, then v by c is very small. V square by c square is much smaller, then we can neglect v square by c square with respect to 1. Therefore, m equals to m naught. But here, and when we are talking about an electron, its mass, sorry, its velocity cannot be very very small with respect to c. Therefore, it remains. So this is your m. Then v equals to m naught c. Now m naught cancel out. So what you have? You have. So I am taking this portion, denominator 1 minus. Just a second. C by root 2. Very good. C by root 2. Let's see. So it is 1 minus v square by c square equals to, this comes here, so it will be v by c square. That means v square by c square. So what we get? Twice v square by c square equals to 1. That means v square equals to c square by 2. I am writing all the steps, which is not actually required. So v equals to c by root. That means 1 by root 2 is almost 0.707 into velocity of light 3 into 10 to the power 8. Calculate it, this meter per second. That is your v. And you observe, this v is not small enough. It is only a fraction of 3 into 10 to the power 8. So if you do the calculation, it will be some value into 10 to the power 7 meter per second. So it's not negligible value, and that's why this part remains m dot by root over 1 minus v square by c square as m. Okay, so be careful whenever you are dealing with subatomic particles. Last problem, same. The question is, what is the de Broglie wavelength? What is the de Broglie wavelength of an electron which is accelerated by a potential difference of 100 volt? This is an end semester exam backout question. The question is, what is the de Broglie wavelength of an electron which has been accelerated with a potential difference of 100 volt? Okay. That means we are talking about electron. So that means the formula of lambda that should be used must be obtained relativistically. So lambda, if you go back, this is the formula. This is the formula we should use, because here lambda is connected with potential difference V, and this formula is obtained relativistically. So we use this formula. So what is the formula? Hc by root over. I always remember in terms of kinetic energy. That means it is Ek. Ek means Ev. Then Ev plus twice m naught c square, twice of rest mass energy. So this is the formula. Now put the values. 6.626 10 to the power minus 34, 3 into 10 to the power 8, 1.6 10 to the power minus 7. That's a root over 1.6 into 10 to the power minus 19. V is 100 volt, 10 square. 1.6 into 10 to the power minus 19 into 10 square plus twice 9.1 into 10 to the power minus 31 into 3 into 10 to the power 8 squared in meter. Do the calculation and tell me the result.
1.23 angstrom.
1.23.
Angstrom.
Very good. So here you observe, actually the question is very easy. If you know the formula, you can get the answer. But my suggestion, please do the calculation by yourself. Each and everyone should do the calculation. Because you are observing, you have to deal with a large number of data. And as an engineer, you have to do it for the rest of your life. So start handling with a number of data, especially with some large power or very small power. So this is one type of problem that you will encounter in Broglie hypothesis.
Hello, sir. Sir, I want to ask something that can we use lambda equals to 12.27 by root V?
Okay. The problem is
Why
that
we are not using that formula?
okay, we are not using that because that formula is derived with the Newtonian concept. That formula is derived with Newtonian concept. That means that is not considered for particles within the atoms. Please mute it. What I want to say that the formula, this formula you want to say, this formula 12.27 by root V is very simple formula, but the problem is this formula is derived from the concept of Newtonian mechanics, where the kinetic energy is simply related with momentum by this formula. Okay. Whereas in relativistic mechanics, the total energy is sum of kinetic energy and rest mass energy. And from that concept, we have obtained that formula. So what is the basic difference? Basic difference is that for normal particles, that means whatever particles you can see, I'm giving the point C, when the particles you can see, that means the particles around us, for them Newtonian mechanics is sufficient. But if the particle is very small, like subatomic particle, then this approach of Newtonian mechanics cannot be utilized. We cannot use Newtonian mechanics for those particles. For subatomic particles, we cannot use it. There we have to use relativistic mechanics. Why? Because for our general particle, their masses are always constant. There is no concept of rest mass energy for them. Whereas whenever we talk about the small particles, due to their smallness, the rest mass energy becomes very crucial. This concept of rest mass energy, m naught c square, becomes very, very crucial. And due to the presence of that rest mass energy, the value of wavelength will be altered. That's why if this question was not for an electron, if this is not for an electron, we can utilize it. Suppose instead of electron, it was said a ping pong ball. We can use it. 12.27 by root v angstrom, we can use it easily. But since it is a subatomic particle, electron is asked, that's why we have to use relativistic formula. We have no other option. In fact, if you use 12.27 by root v, calculate the value. Calculate that value. 12.27 by root v means this one. What the value you get? 1.23, actually 227 angstrom, which in this case almost equals to 1.23 angstrom. But the point is precision. Here, if you observe the other values, if you this means this rough value, if we take the actual value, it will be of the order of, say, it will be of 1.227 angstroms, sir. So you observe third decimal points. From third up to third decimal points, the value is same. From third decimal onward, the value will be changed. And I am not taking any chance. This value we are getting almost same because of this 100 volt. For this particular 100 volt, we are getting the values almost same. We may not get the same values when the when this value, this voltage is different. So it is always wiser to use this formula. Now at the exam, suppose you forget the value, you forgot the actual formula, you forgot this formula, then you can use the formula of normal case 12.27 by root v angstrom, because for a particular value of v, you may get the same value as obtained here. You may get the same value, or if you may not get the same value, then also your value will be very close to the actual value. It will be very close to the actual value, but not the actual value. So my suggestion, if you can remember the formula or you can derive the formula, then always use this formula. Otherwise, use it.
Okay, sir.
Now suppose the question is the energy of the electron is supplied. Energy of the electron is supplied as, say, a large value, say 1 megajoule, a high energy supplied, a high amount of energy supplied. Okay. Now you are asked to find out the wavelength. Again, the same condition. You can use the relativistic or non-relativistic. My suggestion is always for using the relativistic formula. So lambda will be equals to hc. Just a second. hc. Now energy is supplied, not the potential. So our formula will be ek plus twice m naught c square. This is the formula. So put the values: 6.626 10 to the power minus 34 as before, into 3 into 10 to the power 8 by Ek is given as 1 megajoule. Megajoule means 1 megajoule means
10 to the power 6.
10 to the power 6. So you will put 10 to the power 6 here. 10 to the power 6 plus twice m naught 9.1 into 10 to the power minus 31 into c square, 9 into 10 to the power 16. So do the calculation, get the result, check with normal formula whether you are getting any close to it. Similarly, instead of 1 megajoule, suppose energy is supplied as say 1 mega electron volt. What will be the change? Instead of 1 megajoule, now it is said 1 mega electron volt energy supplied. That means what is given actually? What is the value given? Mega electron volt. I cannot hear you.
1.6 into 10 to the power minus 13.
Minus 30. Okay, let's check. Mega means 10 to the power 6. Now electron volt, we know electron volt means if we convert 1 electron volt to joule, then 1.6 into 10 to the minus 19. Remember, we have converted joule to electron volt by dividing joule by 1.6 into 10 to the minus 19. So it is 1.6 into 10 to the minus 13 joule that is supplied. Be careful. Be careful what is given. So that will be the type of questions here. So in summary, what we have learned in de Broglie hypothesis. First, what is de Broglie hypothesis? That whenever a particle is in motion, there will be a wave associated with that, and the wavelength of that wave is lambda equals to h by p. So by this de Broglie hypothesis, we can connect the wave nature to particle nature, and it is only applicable for particle in motion. Doesn't depend on the other nature of the particle. Whether particle has some charge, particle is small, particle is big, it doesn't matter. When we're talking about the theory, it only requires the particle is in motion. Then we have derived this de Broglie hypothesis from the concept of photons energy. That means from E equals to h nu, we have derived it. We have also derived this formula from Bohr's theory. So my point is, all these formulas, all these laws are interrelated to each other. Then we have written this de Broglie wavelength in defined form. So that instead of momentum, if kinetic energy or potential difference is supplied to us, then also we can calculate the de Broglie wavelength. That's why we have written lambda in terms of kinetic energy. We have written in terms of potential difference for non-relativistic cases. That means when we are talking about particles which are not essentially subatomic particles. That means for normal particles, which we can see, which we can feel. On the other hand, for relativistic particles, that means the particles which are very, very small, like subatomic particles, electrons, protons, for them also we have estimated the de Broglie wavelength in terms of kinetic energy of the particles, as well as potential difference applied on those particles. Then we have observed the experiment, how by experimental verification of de Broglie hypothesis can be done. That means Davisson Germer experiment, experimental setup we have observed and how the experiment was done. Then we have estimated lambda, one from de Broglie hypothesis and another from Bragg's law, and we have observed that two values are very close to each other. Then we have done some problems, typically with one type with the case where de Broglie wavelength is same as Compton wavelength. For that, we have estimated kinetic energy, or we can estimate the velocity of that electron for which that condition is satisfied. That means this de Broglie wavelength and Compton wavelength are same. There's a particular case that I have shown you. These are all to understand the concept and how to use it. And if numerical values are given either in terms of potential difference or in terms of energy, we can use the formula to get the value of lambda. And again, my suggestion, if you can remember the relativistic formula, use it to get the more accurate result. If you cannot remember at the time of exam, then use the normal formula. Still, at least you will get some value which will be near about the actual value.